Hello, good afternoon. Thank you very much for attending this last talk of Scala Days. I can imagine that all your heads are quite full after 2 full days, and hopefully I'm able to top it off with the last bit of information. I'm going to talk about building high available systems with Akka Distributed Data. I work for Trivento, which is a consultancy in Akka and Scala in the Netherlands, and currently I'm implementing this at ING. Please remember to rate my talk after this presentation so I can learn from that. So my presentation is essentially split into 3 parts. And the first part, I will give an overview of the problem space of what we're talking about distributed systems and what problems may arise. And then we're going to look further into CRDTs. During this conference, CRDTs were mentioned a few times, and hopefully I can give you some more meaning to know what a CRDT is and how it works. And last but not least, I will take you through Akka and show you how you can use it within Akka to build high available systems. So what does it mean when you're building distributed systems? You have systems spread over multiple nodes, and you may or may not know this, the 8 fallacies of distributed computing. If you don't, read this paper, it's really interesting. It shows you that when you go into the space of distributed computing, that all kinds of things can go wrong, and that we have to think about that in a different way. And one of the things is that the network might not be as reliable as you think it is, even though you're within the same data center. Even then, the network might not be reliable. So this may lead that when you're having a distributed system, and in this case we have a 3-node system, that there might be some partitioning or nodes may crash. And what will happen then? What kind of reaction may, in this case, A or B, get from the system? What's going to happen? And more of that, imagine when you're in a train with your smartphone, putting groceries in the grocery list, and your spouse at home is doing the same thing, and you want to collaborate, right? But the phone and the network is really, really unreliable. So at one moment you drive into a tunnel and you lose connection, but you still want to continue on with putting stuff in your grocery list, removing stuff from your grocery list. But when you exit the tunnel and your connection is reestablished, you want that to be synchronized again with the server and with the work that your other part had done. So up comes the CAP theorem, which essentially states that in a distributed system, you have partitions that may occur, right? So then goes the thing, when a partition happens, what do you want the system to behave, in what way you want the system to behave? And you can either choose for consistency, which means that when you interact with the system, you want it to be consistent so that when someone puts it in and someone else reads, they get the same behavior, and there's no way to mutate it in such a way that there is a conflict within the state in the system. The other thing is availability, when you say, well, I want my system to always be available, right? So when we have a partition, I want my system to continue on working, the thing that cannot be done when you have a consistent system, because a partition, when a system is split up into 2, and you would be allowed to continue on working, would allow for inconsistency. So you see that those are a little bit, you have to choose what you want. Do you want availability or consistency during your partition? So what does it mean to have consistency? There are all different kinds of algorithms out there. Maybe you know some Paxos, Raft, and Zap. All algorithms that are aimed at giving consistency within a distributed system. And it means that you cannot lose too many nodes within your system. And that might feel like, well, when I have a 7-node cluster, I can lose 3 of my nodes and I still am available. And that's true, so that's high available. But you also might get some partitions. And when you're in the minority part of a partition, that means that the system cannot operate in that minority part. So when your system is large and you always want to continue on working, then you see here with consistency you have a problem, because you always need to gain access to the majority of the partition. On the other hand, there is eventual consistency. And eventually consistency allows for inconsistencies, as it states, right? So eventually, in the end, it will be consistent, but there might be moments in time where it's inconsistent. As you can see below, that the two persons have a different view of the world. That allows for a system to be completely separated from each other. As long as you can reach one node, you can do your work. You can continue on putting information in the system, getting information out of the system. Like in the grocery list example. You can still add items to your list and remove items from your list. But to be able to do that, we need some non-conflicting merging algorithm. And that's the thing where it all evolves around. And we'll go into more detail about what that means. So we all know, right, if we all use probably something like GitHub or Git for a versioning system. We start out with some file with hello world in it, and two people split off, change the file, one to hello Scala Days, and the other one was they changed it to hello Copenhagen. And at one moment, it needs to be merged, and we have a merge conflict which we need to resolve, right? And that's reasonable because in our system with software, the order might be really important, and even when it would be combined, it might not work, not even compile. So we cannot have that in a distributed system where it needs to continuously work, right? There is no way that you want to have a ping in the middle of the night, well, this merge has a conflict, please resolve it for me. It should always automatically merge. And that's what it means, that it has a non-conflicting merge algorithm. But how do we do that? And what kind of mechanisms are there? And that's where the CRDTs come around. And CRDT stands for conflict-free replicated data type. So it's essentially in the name, there's no conflict in this data type, or it's resolved deterministically. So there are two types of CRDTs. One type is the operation-based, where each mutation on your data type is an operation. And the operation has to be propagated to all the other nodes in your cluster. So the thing with this kind of CRDT is that the actions are not idempotent. So you need to make sure that you have some mechanism which makes sure that a message, an operation, is only delivered once at that CRDT. So you need some orchestration around that. The other one is the state-based CRDTs, and that's the one we're going to look more into detail today. The state-based CRDT is essentially a full state sent around to the other nodes. And by sending this full state, you get the feeling that you get a lot of data over the wire, right? So there are some optimizations, and there's an optimization paper, efficient state-based CRDTs, by using delta mutations. And I'm really glad that it is part of Akka since recently. In a state-based CRDT, you have essentially three operations. You can query it to get the information out of it. You can do updates on the operation, on the data set. And also you can have this merge operation, right? I have my state, I receive state from the other, and I have to merge that. So the merge is really important here, and we're going to look into detail in the next slide. So merges, and this is really important, needs to be commutative, associative, and idempotent. So it doesn't matter if an incoming data full state is merged multiple times, or in what order you receive it from other nodes. Essentially, in the end, the merge is deterministically, and both sides will merge into the same end state eventually. So let's look at a very simple data structure, which is really familiar. It's the vector clock or vector version. So this is when you hear vector version, this is essentially it. And in essence, it's like we maintain one integer, right? So if we, with all the audience, we maintain one integer, and everyone in this audience can increment that integer. But we need to communicate with each other to find out what the current value of the integer is. So it's infeasible to have this mutable state, right? Because we can have partitions where you cannot communicate with each other, and we may have different parties. So when we talk to each other, we need some mechanism to be able to communicate with each other and just communicate information with each other, so that in the end we can end up all together in the same end state if no further mutations would be done. So the thing is, the data structure is like an array. And in the array, every node has its own place. And you can only mutate your own number. So there's no way you have a conflict then, because everyone can only mutate its own number. So if I want to increment my number in the increment function, I look up my own place in the array and increment that with the number I would like. So in this case, it would be incremented with 1. If I want to merge, I'm going to show you how that works. So let's imagine this example, and there are 3 nodes. And as you can see, to get the value of the data set currently, you have to add up every individual number, right? So in this case, we have 3 nodes. Each node has its own number, and if you add them all together, you get the total, the current value of the number. So imagine it would be counting number of clicks somewhere, right? So currently, they are completely diverged. A thinks it's 14, B thinks it's 17, and C thinks the current value is 16. So now B is going to send its full state to node A. So when that happens, the merge will happen, and that's the formula which stated up there. And what it does, from each position in the array, it will take the max value. Because you can only increment, if you take the max value, you have the most recent information. So if I merge these, A and B together, the max of 3 and 3 will be 3, the max of 5 and 7 will be 7, and the max of 6 and 7 will also be 7. So A has new information, and now it has the new value of 377, and as a current value, it's 17. And imagine now that C sends its information to node B. The same merging will happen, and you'll see that when we take the max of 3 and 1, it's 3, max of 7 and 6, 7, max of 7 and 9 is 9. So what happened now is that C had incremented its own value. As you can see, it had more recent information than the other nodes. And its information, that 9, is now propagated to node B. But node A didn't receive that information yet. So still, you see now that node A and B are out of sync, because B has more recent information from a node which A didn't receive. So if we continue this example, and A sends its information to node C, then we see that it was doing the same way, like maxing every number. And even after one step of giving each other information, we're still out of sync. So now we continue on this operation, and B will send its information again to node A in this example. So what now happens is that the information it got from node C will transitively be given to node A, because node B merged the information of node C in its own data set, and now the full state will be transmitted to node A. So the information from node C is now propagated to node A. If we do the same thing for the information to node C, you will see that node C will also merge. And node B will no longer need information, but it can get information, right? It's idempotent. If it would receive information again from node A, for instance, you'll see that node B already has the most recent value, so would be no change in the data structure. So you see that after 2 steps that there are converged, and that they now arrived all at the value of 19. The value which didn't exist at the first place here, right? So this is the thing. Now it's completely merged, and it's never possible to have a conflict. So hopefully I'm able to explain it well enough that you can see that there's no possibility for conflict, and it can always merge, and they will derive at its end information. So that was a little bit basic of CRDT. We'll get into detail a little bit more with another data structure. But now we're going to look at Akka Distributed Data. Because Akka has a mechanism for CRDTs implemented, and it's called Akka Distributed Data. And Akka Distributed Data is based on the full state CRDTs. So it will gossip the full state to the other nodes, right? And as I mentioned before, thanks to fantastic work also by John and Patrick, there's now delta CRDTs within Akka, so that it can mitigate the amount of information it will send, and it will be sending deltas as much as possible. The way Akka distributes the data is with the gossip protocol, which means that it randomly picks a node in the cluster to send it the full state. And this randomness will eventually be made sure that every node will receive the information, right? So you gossip it to one node, that node will randomly gossip it. So transitively, it will distribute all over the cluster. And it seems to be that this is fairly nice way to do it, because you don't need any orchestration for it, and it works quite decent. The thing with Akka Distributed Data is that every node in the cluster has the full state. So everybody knows the complete data set, which means that it has to fit into memory. And that's really important to remember. So how does it work with Akka Distributed Data? How can I operate with it? As we know, and I've seen hands in a lot of rooms, that almost everybody is using Akka. Akka evolves around actors. So it would be no surprise that the replicator is an actor you operate with. And the replicator is in essence the receptionist which gives you access to your data. So this means that everything is completely asynchronous within the structure. The replicator can be acquired via the distributed data extension, which you can acquire with the line below and ask for the replicator. And once you get this replicator, you are set up to start communicating with your data and set your data up. So the interface is, the protocol is that you can send 3 commands to it. The first one being that you can get information out of it. So if there's information in your data structure, you can say, well, give me this specific data structure, because it's like a receptionist. You can have multiple data structures. So you can say, well, give me this data structure, and it will retrieve that for you. The other thing is that you can update. You can change it by sending the update command to it, and we will a little bit look more into detail about how that works. But essentially, you will send a message to the replicator, well, hey, I want to update this, this data structure and do it in this way. And you can delete, completely remove a data structure from your propagation, from your set. But the thing is that it will leave around some tombstone, which will never leave. So it will always be there, and you cannot undo it. So once you delete a data structure, that position in memory, so to say, is gone, and you can no longer reuse that. As stated below, all commands need a key, and the key is the key to your data structure. So we saw the grow-only counter. Say I have 2 different grow-only counters, and so I have 2 different keys to access these data structures. I can specify a consistency level. So I can say, write this to 1 node when I do an update, or write this to a majority of nodes. And I will show you later on what it exactly means to use those consistency levels. And with read, it goes the same way. You can also read from multiple nodes and get the most recent information back. And the last thing you can do is you can put context on your request. So I got a request from some actor. I have to do something, I go to the replicator, but I don't want to lose this context, right? So I can put that into the context information, what was the requester and what was the message that was sent to me. And I will get that back with the response from the replicator, so I can respond to that actor. So I promised to look at the update function. And the update function has the properties I showed in the previous slide. But it also needs an initial value, which gets used when you update some data structure and it's not there. So again, this grow only counter, when I want to use it, but there's the first time it's not there, how do I want to instantiate it? What's the initial value? And a modify function. So the modification is done on the other side, right? So I send the update function with the modification function to the replicator, and there it will be applied to the data structure. So if we look at this, this command, I have an OR set, and think of an OR set just like a plain set. You can put elements in it, and you can remove elements from it. It's an OR set, which means observe remove, and later on I will go into more detail about that. But for now, it's just the set structure, and it contains strings, as you can see in the type. And the key to the place where it is a string and its conferences in this case. So when it's not there, I give an initial value, which is the empty set. And in this case, my consistency level is right local. So it will be applied to your local CRDT, and then come back to you with the result, with the message that it succeeded. And the context, as you see here, and I put the sender in, and the request I got in, and that's the thing I will get back. The last thing you need to specify is then what happens on your OR set, because you can not only add elements to it, remove elements from it, but you can do all kinds of stuff with it, right? So in this function, you can have a mutation on your OR set and give that as a result. It will be applied to your data structure. And it will capture the changes and will propagate that with the delta replication or with the full state. It will propagate it to the other nodes. When you create this command, you send it to the replicator, and you will get, eventually you will get back a response that your update was applied. So I mentioned consistency, but I also talked about that this is not about strong consistency, it's about eventually consistency. So what does this consistency mean? You can specify a write and a read consistency, and there are different things you can specify. As mentioned in the previous slide, you can say, I'll only apply it on the node I send this information to, on my own local node. But you can also say read or write to n nodes, right? So if you have a 7-node cluster, you can say, oh, I want it to 2 nodes, so that I know that it's at least propagated to one other node, hopefully, and that hopefully I will explain. So that the information is already at different places to prevent some crashing situations or something. A majority, so to the quorum, or to all nodes. So might it lead to a consistent system when you say, okay, I write to a quorum, I read from a quorum. So if that works, right, if the happy flow, you will write to a majority, read from a majority, so that will make sure that you will always get at least one node with the most recent information, and then you have some form of consistency, right? But there are all different failure scenarios, which might mean that it didn't get that far, or it did get that far, so you're not really sure. So as stated in red here, a failure getting back from the replicator might not mean that it's not applied. And I will show you in the next slides what that means. So imagine that I have this 3-node cluster. And in the current set, I have X and Y. And I say write to a majority and add Z to the set. So what will happen is that it will first apply Z to the local set. It will put it in my local set so it's there. And then it will start with propagating that to other nodes. But hey, I have a network partitioning. So even though I tried to replicate this information, it didn't work. So it failed. Fortunately, Akka has some fallback implemented that if within the time bounds, it has some time left, it will try the other node. So in this 3-node cluster, it will say, well, apparently the blue node doesn't respond. Let's try the green node. Maybe that one will respond, and then I still have my quorum. But it doesn't work, so essentially in the end, it will say, sorry, I failed, I couldn't send it to the other nodes in time. Okay, but now you see that in the orange node on the bottom, Z is there. It's not reverted. And it's also really difficult to revert that. In the local situation, it would be maybe possible, but if it's already distributed to some nodes, say I have a 7-node cluster and I couldn't reach the quorum but one other node, do I know which node I reached out to? Am I sure that I can undo it, that I can reach it when I want to undo information? So there's no rollback in that sense. So now the network partitioning is resolved, and Akka Distributed Data has this gossip protocol, so it will gossip the information, in this case, to the blue node. And now a user comes along and asks for the information, and it will get the set X, Y, and Z. So even though we got a failure by putting Z into the set, you see that in the end, it's still in the set, it will be propagated in this situation. There are also failure situations when the orange node would have failed completely now, then we lost the information, right? Okay, there are quite a few data types within Akka which you can utilize for your application. So I showed you the grow-only counter in the beginning of the presentation as a CRDT. But there's also a PN counter where you can not only increment the value, but also decrement the value. There are different registers. There's the last write win register and as a flag, which you can set once and only once. There are two kinds of sets. The grow set is maybe the most easiest because it's just a set, right? So if there are multiple nodes putting information in the set, it's hopefully easy to see that when you merge that, you take the union of the two sets, and because you never remove information from the set, it's always able to merge that to information. But what about OR, observed remove set? How does that work? I will show you in detail. And then there are a few maps. An observe remove map is essentially the building block of the map structure. And you have the OR multi-map, where the value in the map is an OR set. So essentially in a map, you need a key and a value, right? And when you need to propagate a map, you can match on the key, so the key doesn't need to be merged, because that's given. You want to merge the things in the same key. But then the values need to be merged. So the values need to be a replicated data type. So in the OR multi-map, it's an OR set. In the last write win map, it's an LWW register. And in the PN counter map, it will be a positive-negative counter in that map. In the map, you can use any value for a key. Since 2.5, in 2.4 it needed to be a string, but currently you can use any value as long as it's serializable over the wire. And you can create your own data structures. So what I said, the values need to be serializable, but also the data sets need to be serializable. And whatever you do not use Java serialization. So, custom data types. You can implement your own data type. When the given data types are not sufficient for you, you can implement your own. And what you need to implement is the replicated data type trait, and then you need to implement this merge function, where you need to implement this merge, and it needs to abide to the rules given previously on the slide that need to be idempotent, associative, and commutative. So it needs to be a deterministic algorithm that always gives the same result, right? But as mentioned, there's also this replicated data type structure where the deltas get replicated. And all the Akka internals are able to do the delta replication. But you can also put that on your own data structure. And then you have to implement these three methods where the most important one I will handle is the merge delta, where you receive deltas from other nodes, and you need to merge that with your own data structure, and as a result, give the new data structure. And the way Akka works is that it will send these deltas, and you will be able to apply that. But if you miss deltas, for instance, it will, in the end, fall back to the full data replication. So it's an optimization with the fallback to the full data replication so that you're really safe, that you won't lose information or that you get stuck in some situation. So again, it's all in memory. So also beware of your data structure, what you're doing. What can you do when you merge information that you can compress it? So for instance, in OR set, dotted version factors are used to compress it and to make sure that we get a least amount of memory footprint. So again, when you create your own custom data type, it needs to be serializable, but whatever you do, make sure that you don't use Java serialization. The observed remove set. I said in, a few slides ago that a simple set, the grow only set, is quite simple because the merge is simple, the union. But how do we go about it when we want to remove items from a set? What information do we need to propagate to the other nodes? So in this example below, you'll see two nodes, and you see a picture of what the data set will look like. So in the top, you see a version factor. So the data set has a version factor of its own, which is the current version you know of the data. In this case, they are in sync, and they are both at version 2.1. Every element in this set has its own version factor. So you know in which version an element got added to the set. So now, let's say node 1 removes an element from the set. So it removes element A. And it does so by simply removing that from the set and incrementing the version factor. And remember, you only increment your own number. So in this case, for node 1, it's the first position in this array. So it will increment that to 3. So it has a new version of the data with A removed. But there's nowhere stated that A is actually removed. It just removed it from the set. Remember that. Now node 2. Node 2 does a more simple operation. It adds Z to the set. So it does so by incrementing the version factor and taking that for the version factor for the element, so that it knows in this version Z got added. And now we're going to look at how that works out when it gets synchronized. So node 2 will send its information to node 1. And the thing it does is that it will need to merge these sets. So first off, the easy thing is to see what information is in both sets, so that you get an intersection, and then you get B and G, which are in both sets. Then we are left with two elements. Element A. Element A is no longer in the set which is in node 1, but it is in the set of node 2. And the version of A in node 2 is 1.0. But currently, I'm at version 3.1, and I get a version of 2.2, and so I'm sure that this was in both sets, and they all seen A. So it's no longer there, so it can be removed. Z is a new element, so it can simply be added. And the same goes the other way around. Node 2 will receive this set where it's missing element A. I'll say, hey, A is missing, but I'm getting this version 3.1 from node 1, so I'm positive that it at one moment had seen element A. Does that make sense? Silence. So hopefully you're silent because you don't want to speak up. Hopefully you can see, and otherwise come by, I can explain more in detail if you want to. You can deduct from this that node 1 must have removed this element from the set, right? Okay, so if we look at Akka Distributed Data and CRDTs in general, there are some limitations, right? So it's not suited for systems where you need consistency. Because even though we have consistency levels, it doesn't give you strong consistency in any way. So if you really need consistency, look for other systems. And it's not suitable for big data, at least not out of the box. And as it keeps everything in memory, it will run out of memory. Every node is the same, so it will keep everything in memory. And the gossip protocol sends out the full CRDTs. In the end, it will send out the full CRDTs at one moment, right? So when the node starts up, it will essentially receive the full state. So you have to remember that it's based on full state, and there are optimizations with, by using deltas. But it also means that when you get really big data structures that need to be replicated, that it has impact on your system. So what are the use cases for CRDTs? Well, you can use it for service discovery. Well, that's what we are doing at ING, because that's a system where you don't need consistency. But also for your grocery list, as I gave in this example. You don't need consistency in your grocery list, you want to cooperate. So essentially, in every collaboration situation, you might want to have eventual consistent situation. Google Docs is using CRDTs underwater to communicate and be able to send over information, be able to continue on working when you're offline and synchronize when you're back online. There are databases using this, social media, I heard something about gaming. There are a lot of use cases, but you need to remember it's eventual consistency geared towards being always available, being able to always serve your customer. So I showed quite a lot, and what I want to do is dive a little bit into code and show you how little code you need to use this in your own system, right? Exit this, and turn off mirroring. Turn on mirroring. So what I have here currently, we'll go into presentation mode. This is a simple actor. As you all might know, there's this actor, and I've implemented my data set as a simple set, a simple Scala set. I can receive commands, I can receive a get command, where I can reply with the information within the data set by filtering by name. And I can register services by adding them to the set. But as you can see, there's no way that if I spin up multiple nodes that they are able to know from each other what's in the set. So if I spin up 2 nodes, put the information here, it will never end up in the other nodes, right? So what you need to do is start with adding the replicator. Right, and as I said, the replicator is in the distributed data extension where you can get the replicator. The replicator also for certain because it needs this vector, right? So it needs to know who you are. It needs to have implicitly the node, the cluster information in scope, so that you know which place in the cluster, in the structure you have. You might remember that I said that you need a key. So in this case, we're going to use an OR set, and I name it services in that OR set. So now I need to implement this protocol for getting information. So this is quite a bit. So first off, what I said, you need to send this GET request to the replicator. Right? You say, well, I want to have access to this information. Give me the services key, give me access to the OR set with services. Only read from the local key store, and well, here's my context. You will then get back either 2 things. You will get back a success. It got the information from the local store. Here you are. This is your key, and this is your context. And from the result, you can get the elements. Right? And then when you have these elements, this is simply a set again. So then you can do your operations and filter by name and respond in the end to the original sender, which is out of the context. But it can also happen that it's not found. in this case. Also, we have this registration. So on the slides, I showed you already how the update function looks like. And you have to implement it here. And what I say here is just add a service to the set. So you will get back one of three messages: an update success, everything went right, I updated information for you. But depending on what happens, you might have a failure in your function, for instance, then you can get back a modification failure, which means the function you have specified gave an exception. Or you can get an update timeout, and that's what happens when you say, well, write to a quorum, but you cannot reach the quorum. Then you will get back in the end the timeout, sorry, I couldn't reach the quorum in time. Okay, so that is one thing. The other thing we need to do, we need to create a cluster. So you need the cluster actref provider. And of course, we use Java serialization. So essentially, that's the thing I've implemented. What I didn't show you was the Akka HTTP front end. I don't want to bother you with that because the essence is in this actor. So now I'm going to start two nodes in two different windows. So first start the first one. So it started, and start the second one. And what will happen is that they will find each other, right, like the Akka cluster, and when they find each other, they will start doing gossiping. So first off, when I say, I didn't know if you saw that, but I started on two different ports, 8080 and 8081. If I get the information from either one, there will be no information in there. But what I can do is I can put information, let's do it on 8080, and I don't know if you know HTTP, but it's a really easy tool to put JSON over the wire. In this sense, we're posting to my service, and it will create a JSON where host will be different, and the port will be 9876. So now, if I go to 8080, I will get back my service I just put in. And if I go to 8081, I will also get the information back. So now it's propagated. And also, when I shut it down, I start it back up. You'll see that it's, in this case, it was really fast. Sometimes you will see that when you get there, you didn't receive a gossip yet. So it will be empty. And then after some time, it will converge again, like it's eventually consistent, and then it will be the same in every node. So the gist of this is that it's fairly simple to start using this in your project. So that leads me to the end of my presentation, and hopefully I was able to express it clearly enough for you to understand what this all means and how you can use it. Are there any questions?
My question about what shall I do when I get update timeout? Because as far as I understand, I can't retry again, and I can't revert back, so what can I do?
You certainly can retry. It might be the case that it's resolved again, and you might be propagated. So, there's no definite answer to that. So it depends on your model, right? So you know that you put it there, on best effort, it gets propagated. So hopefully you will get back a success, and then you know, okay, it's propagated, I'm safe, and I know that I'm now in some sort of way of consistency. If it doesn't work, you have to think about what will happen, because there are different scenarios. Either only on the local node, you get a failure back and the local node crashes, so it seems like it never happened. Or, like in my presentation, the situation resolved and it is propagated. And in your domain model, you need to think, well, if that happens, how do I resolve it? What do I want? How do I want the system to be resolved? What do I need? So I'm sorry, I cannot give you a definite answer.
Thank you.
Hey, thanks for the talk. Is it possible to back the replicated data like with a persistent store or something? So in case the whole cluster goes down and comes back up, you want it to be in like the same state as previously or whatever?
Yes, excellent question. Yes, Akka has persistence in it, so you can flip it on, and then we'll use level_db to persist information on the local disk of that node. So yes, it's there.
Cool. Thanks.
No other questions? Okay, thank you, and then I will leave you to beer.